classes on fundamentals of electrical circuits. We are still on module 2, where we are looking at electrical machines. We had 2 sections in DC machines, and then 2 sections in transformers, and 2 sections in induction machines, and this is the last of the sessions in induction machines. We discussed basics, slip and speed, the torque of induction motors, then starters, then again single phase induction motors, and finally now we are looking at the efficiency and losses, the most important, another important component of discussion that needs to be there when we understand the fundamentals of induction machines. So let's start from the very beginning. In this problem, in this question, the induction motor for induction motor operating at slip S, the ratio of gross power output to air gap power is equal to. Okay, so this is a basic kind of question wherein we understand that there is a power input, electrical power input into the stator of an induction motor, and what happens is that there is a component which is the core loss, and then another component which is the stator copper loss. The rest goes into the air gap as rotor input, and S times this rotor input goes off as copper loss, and so the rest is now available as gross power input, okay, as the power output of the induction motor. And of this, friction and mid-range losses are also removed, and then you have the final output of the induction motor as the torque of the machine. Okay, so this is the general trend, okay, from which different aspects can be identified as we go through the problems. Okay, so let's look at this problem where the ratio of the gross power output. So gross power output is the power input being given to the rotor or to the air gap, multiplied by 1 minus S is giving us the gross power output. Okay, so it is so the ratio of gross power output to air gap plus flux is going to be 1 minus S, or option B. Okay. The second question is wherein a no load test is conducted on a 3-phase induction motor at different supply voltages. The supply voltages are changing, and the plot of input power versus voltage was drawn. Okay, so input power is now changing because the voltage is changing. Okay, and the voltage and the voltage is different at different contexts, but at the same time, if the machine is moving, something that has to be given to the motor is always going to be the friction and windage loss. Okay, so this is again a question with respect to the losses on a machine. Okay, so this is so if you are this curve was extrapolated to intersect the y-axis, so the y-axis will yield the constant power that has to be supplied to the motor or to the input, such that the friction and windage losses can be met. Okay, so the intersection point yields the last of the answers, that is the friction and windage loss. It's not the core loss, okay, because core loss varies as the voltage. Both the stator as also the stray losses vary. The stator copper loss, everything varies according to the voltage. Okay, so that's it. So extrapolation will not give you a constant loss like the friction and windage loss. Okay. So now we move to the third question, wherein a 400 volt 50 hertz 30 horsepower 3-phase induction motor is drawing 50 amps. Okay, so it's drawing 50 amps at 0.8 power factor lagging. Okay, so 400 volt 50 hertz 50 amps, and then again 0.8. So we know the power input that the machine is taking, which is √3 VLIL cos phi. Okay, the stator and copper loss, and then the losses are now going to be deducted. That is, we have stator and copper losses 1.5 kilowatt and 900 watt respectively. The friction and windage losses are 1050 watts, and core losses are 1200. So the first loss that has to be removed is 1200. Then we have the stator copper loss, which is equal to 1.5 kilowatt. The rest is now given to the rotor or the air gap, and then 900 watt as also 1050 are removed to get the total output. Okay, so and 30 HP is referring to the output that is possible, but of course now the machine is in a different context altogether. Let's see. So the power input is given by √3 VLIL cos phi, okay, divided by 1000 to talk about the kilowatt context. So we have 27.712 as the input to the machine. Okay, so yeah, so that's one thing. Second is core law. Okay, so now what is asked is the friction will, okay, the air gap power. The air gap power will remove from the input only the core loss as also the stator copper loss. So the core loss and stator copper loss together amounts to 2.7 kilowatt. So once you remove it, you get air gap power as 27.712 minus 2.7 or 25.01 kilowatt, or C option. Okay, a simple problem. Okay, this is a little different. A three-phase squirrel cage induction motor has a full load efficiency of 0.8. So efficiency is always given by our output by input. So output is proportional to efficiency into input. Input is considered to be remaining constant. Okay, but output varies. Output varies according to the speed and the torque, because output is given by 2 pi nt by 60. Okay, so all these so two relations need to be remembered. One is 2 pi nt by 60 is equal to power output, and the power output into input is power input is going to be the efficiency. Okay, so let's move further. So it has a full load efficiency of 0.8, okay, and a maximum efficiency of 0.9. So these are the two efficiency ranges. One is the full load efficiency of 0.8 and the maximum efficiency of 0.9. It's operated. This machine is operated a slip of 0.6. This is a very poor slip, because now speed is going to come down drastically, because if the synchronous speed which is not given is ns into 1 minus s is going to give us the rotor or the motor speed, which is equal to now only 0.4 times the synchronous speed. Okay, by applying a reduced voltage. So this is the strategy: reduce the voltage and get a lower speed. Okay, the efficiency of the motor at this operating point. So this efficiency is going to be very poor. Why? Because we are running it at a low speed, so the output is affected by both the by both the torque and the speed. Okay, so let's see. So now the options are less than 40%. This seems okay. This seems like a good answer, because efficiency is poor. Greater than 60%, which means that anything can be an answer. In the range of 80%, a 0.8 plus or minus 0.1, or 80 to 90%. Okay, none of the above. None of the above does not seem to be a good answer, but let's see how it goes. Okay, so power output, as was mentioned earlier, is proportional to both the speed and the torque. Okay, it's also proportional, and power input is yeah. So yeah, and power output is also proportional to power input multiplied by the efficiency. Okay, so far so good. And the speed now we see is ns into 1 minus s, and the slip is very poor, so speed is only 40%, 0.4 times 1 minus points is 40%. Okay, so at very low speeds, so now n is only 40% of ns, or 0.4 ns, and at the same time slip at such low speeds, the torque is going to be inversely proportional to speed. So torque is now proportional to 1 by 0.6. It's inversely proportional to speed. Okay, so it's given by 1 by 0. Torque is proportional to 1 by 0.6. Okay? And now the efficiency is varying between 0.8 to 0.9. Okay, so that is between the full load to maximum efficiency. So let's see what happens at s is equal to 0.6. Okay, so we have two ranges. Let's use those ranges. So we can see that the efficiency is now progressing between 0.8, because efficiency is if power output is equal to power input multiplied by efficiency. So efficiency now can range between 0.8 into 0.4, because output is also proportional to speed, and and torque is inversely proportional to speed to slip. So 0.8 multiplied by 0.4 divided by 0.6, this gives you a range of efficiency which is equal to 53.3%. Okay, the other extreme end is 0.9 multiplied by 0.4 again, because speed has reduced to 40%, and the slip has reduced to 60%, so inversely proportional to 0.6. So 0.9 into 0.4 by 0.6. So now the efficiency is ranging between 53.3% to 60%, which is not there in option A, B, C, or A, B, or C. So none of the above seems to be is the best answer. Okay, so it is strange, but it's true. The fifth problem: the power input to a 500 volt, 60 hertz, 50 hertz, 6 pole, 3 phase induction motor. 50 hertz, 6 pole means it is 120 F by P. Yeah, so it is 1000 RPM as NS. Okay, running at 975 RPM. So slip is 1000 minus 975 divided by 1000, which is 2.5%. Okay, is 40 kilowatt. So power input is given as 40 kilowatt. The total stator losses are 1 kilowatt, so that can be deducted. So you get the input to the input to the rotor or input to the air gap, because stator losses include both the copper loss as also the core loss in the stator. If the total friction and windage loss are 2.025, what is the efficiency? Okay, so you get the input to the rotor multiplied by S to get the copper loss, remove that, and then remove also the friction windage losses, then you get the output. Okay, so output by input. Okay, so as simple as that. So first and foremost, we find out NS, which we found out already, which is 1000. We find out S, which is 25 by 1000, which is also 0.025. And then we find out the rotor copper loss as PI into, that's you have to find out PI first. What is PI? Power input to the rotor, which is equal to input minus stator losses, which is 40 minus 1, that is equal to 39 kilowatt, multiplied by S, you get it as equal to 975 watts. So the power output is the same as equal to 39 minus the copper loss, which is 0.975 kilowatt, and then remove the friction and windage losses, which is 2.025 kilowatt. So the final result is 36 kilowatt. The final output is 36 kilowatt divided by the input, which is 40 kilowatt, gives you the efficiency is equal to 90. Okay, so as simple as that. So let's move to the sixth problem. Here we have a very complex structure where an auto transformer is feeding power, three-phase 50 hertz power supply to an induction motor. So it's and then it has a shaft connected to the which is giving, so the induction motor is driving a DC generator, which has a field powered by 220 volts, so it's separately excited, and then the DC generator is feeding a resistor. Moreover, the induction motor seems to have a resistive bank, so it could be a slip ring induction motor with the resistors. Okay, so let's read. A three-phase 440 volt 50 hertz 4-pole slip ring induction motor is fed from the rotor side through an auto transformer, and the stator is connected to a variable resistance as shown in the figure. So it should be the state, could be the rotor, not the stator. Okay, the motor is coupled to a 220 volt separately excited DC generator feeding power to a fixed resistance of 10 ohms. So REX is now 10 ohms. Okay, so it is taking the power from the DC generator, which is being driven by the induction motor. Okay, and the other input happens to be the field. Okay, 2 wattmeter method is used to measure the input power to the induction motor. Okay, the variable resistance is adjusted such that the motor records so much of power at 1410 rpm. So the machine is a 4-pole 50 hertz one. So the speed is 15. The synchronous speed is 1500. So and it runs at a speed of 1410 rpm, which means that there's a slip, and the slip is given by 90 divided by 1500 or 6%. Okay, so I suppose that's clear. Okay, and now the watt meters record 1800 and minus 200 watts, which means that the power input to the induction motor is 1800 minus 200 or 1600 watts. Okay, neglecting all losses, so everything can be removed. The DC generator power output. Okay, so what all are, so we realize that the stator gets all of 1600 watts. Okay, and then the gross power output is going to be 1 minus S. So 1600 into 1 minus 0.06 gives you 1504 watt as the output. Okay, so from the different options A, B, C, D, only one answer is 1504, and that's where it, and obviously the current will be given by V square by R is going to be, or no, the I square R is going to be 1504. So just divide by 10, okay, which is REX, and then take the square root. It gives you 12.26 amps as the correct answer. Okay, there's another bit of the problem too. The speed of rotation of stator magnetic field with respect to rotor structure will be, okay. So it is definitely going to be at synchronous speed, which is 1500 rpm, and it's going to be in the opposite direction of rotation. Okay, so it cannot be in the same direction of rotation. Okay, so moving on to the seventh problem. The locked rotor current in a three-phase star connected 15 kilowatt 4-pole 230 volt 50 hertz induction motor. So 4-pole 50 hertz tells us about a 1500 rpm machine, and the synchronous speed at rated conditions 50 amps. So it is taking 50 amps. Okay, and the condition is a locked rotor or blocked rotor condition. Okay, so neglecting losses and magnetizing current, the approximate locked rotor line current drawn when the motor is connected to 230. Now the situation has changed in a different manner. the voltage is changing to 236 volt and frequency is changing to 57 hertz. Okay, so we know that when the machine takes 230 volt, okay, yeah, and what is asked is neglecting losses and magnetizing current, the approximate locked rotor line current. So all the losses can be removed or R can be set as equal to 0, but still we know that the old current 50 amps was drawn when was drawn such that we are having an impedance as given by R plus, where R is equal to 0 plus 314X. Okay, so we are using 314L. Okay, so it is that is X is equal to omega L. Okay, so 314 because earlier it was 50 hertz. Okay, so 230 by 50 is equal to R plus, where R is equal to 0 plus 314L. Okay, so and at the same time we have another condition where 236 is the applied voltage and R is the same, L is equal to 0 plus 357.96. Why 357.96? Because that is going to be omega for the second condition of 57 hertz into L. That gives you new current. Okay, so now just take the ratios. You'll see to put L R equal to 0. You can see that the current has now reduced to 45.004 or 45 ampere is going to be the correct answer. The only change that we have to put here is that omega L is varying between 314 L to 357.96 L. Another aspect happens to be the voltage. So accommodating two changes, the new current is going to be 45 amps. Okay, so let's look at the eighth problem. Three phase 10 kilowatt 400 volt 4 pole 50 hertz star connected induction motor draws 20 amps. Okay, so it is 50 hertz and 4 pole 1000 rpm. It's no load and block rotor test are given below. No load test is at 400 volt. It draws 6 amps as the magnetizing current, and so the stator loss is 1002 watts. Okay, block rotor test is done at 90 volt, but at 15 amps, though the machine is rated for 20 amps. So you have to change that. Okay, because the copper loss is now only 762. Now you have to put it up for 20 amps. So 20 by 15 square multiplied by 762 gives you the full load copper loss is 1.355 kilowatt. Okay, neglecting copper loss in no load test. Okay, of course, and core loss in block rotor test as we do in the experimental stage. Estimate motor's full load efficiency. Very simple. So we see that the output is given as 10 kilowatt. So 10 kilowatt divided by 10 plus all the losses. So what are the different losses? Only two losses are there now. One is 1002 or 1.002 and other is 1.355 kilowatt. So together we have 10 plus 1.002 plus 1.355 as the input. So output by input gives you the efficiency is 80.9, okay, or 81% as B option. So ninth problem, we have an assertion and reason under V by F control of the induction motor, a very important control. The maximum value of the developed torque remains constant over a wide range of speed in the subsynchronous region. Of course, the V by F control is exerted in the subsynchronous region, and you get the max. So this is right. Okay, so and the reason being that the magnetic flux is maintained almost constant at the rated value by keeping the voltage ratio V by F constant over the considered speed range. Okay, so except for the very low frequency times, we are getting what is called as the magnetic flux remaining almost constant. Okay, so both A and B are true as is given in the first option, and R is the reason for it. Okay, this was mentioned even earlier. Moving to the 10th problem. A three-phase induction motor is driving a constant load torque load at rated voltage and frequency. If both voltage and frequency are halved, so V is halved, F is halved, so V by F again is maintained constant. Okay? Following statements relate to the new condition if stated resistor, leakage resistance, and core loss are ignored. So all that may be affected are now ignored. Okay. So what is condition P? Yeah, if the difference between synchronous speed and the actual speed remains same. It does remain same. Why? Because we see that the frequency is halved. Okay, so in both so 120 F by P, so 120 does not change, P does not change, so the relation between synchronous speed and actual speed remains the same. Okay, The air gap flux remains the same. Yes, that's the purpose for V by F control. Okay, the stator current remains the same. Okay, yes, because the frequency is halved and the voltage is also halved, the magnetization current remains the same. Okay, so we have stator current remaining the same. Per unit slip remains the same. No, because it is now a ratio. It is it is a ratio of the ratio to the base speed, just pain is changing. So PQ and R are correct. Okay, and option B hence is correct. Okay, going to 11th problem. The three-phase wound rotor induction motor is to be operated. A three-phase wound rotor induction motor is to be operated with slip energy recovery in the constant torque mode. When it delivers an output of power PO at slip is equal to S, then theoretically the maximum power that is available for recovery at the rotor terminus is equal to it's directly proportional to the rotor copper loss, because that is what is being used for that is what is being recovered as slip recovery scheme. Okay, so we have PO divided by 1 minus S giving us the rotor input multiplied by S giving us the copper loss. Okay, so option D, very simple. Okay, in the last question we have several applications, where in group 1 lists different applications and group 2 lists the motors for these applications, so we have to match them. Okay, choosing the right combination. So some of them might be true, but what is best is what we are going to choose. Okay, so food mixer, if you look at the different options in group 2, the universal motor is definitely going to be the motor applicable to motors, but we can also use others like permanent magnet, etc., but then they happen to be very expensive. So universal motor is the best option. So A, C, and D happen to be okay. Okay, B is rejected. Okay, then we move to the cassette tape recorder. Again, stepper motor is a good option. Then again, yeah, so A seems to be okay, but at the same time we see that yeah, so 3, that is universal motor is not used, but at the same time, yeah, we do use permanent magnet DC motors. Okay, so permanent magnet DC motors are good for cassette tape recorders. In fact, they used to be more prominent there. So perhaps A, and again C as also uh, 2 is single phase induction motor is not used. So A and C may be right. Okay. So moving on to domestic water pump. So domestic water pump inside the house is almost always single phase induction motor. So though we do have 3-phase induction motors for large applications. So a domestic water pump for single phase induction motor means 2. Okay. So 2 is there in C but not there in A talks about three-phase induction motor. Okay, with for very large applications. Okay, so let's see what the escalators are using. Escalators use generally three-phase induction motors. Okay, because they are general purpose and supposed to carry many people, or else you could have used a DC series motor. Okay, but then constant speed is required, so DC speed series motor fails there. So the three-phase induction motors are the best. Okay, so all said and done, option C seems to be the best. And that concludes the last of the sessions in the induction motor induction machines domain. We in this section we were essentially talking about the power scenario in an induction motor. Power input is given for the first leakage or first throwaway happens to be the stator copper loss, stator core loss, and then stator copper loss. So then we arrive at the input input to the rotor at the air gap. From there, SPI or S power input to the rotor is removed for the copper loss. Okay, and then it can also be recovered, and then the remainder goes as the gross power output. But then friction indeed losses are also removed, and then the rest happens to be available as the output. Okay, and efficiency is always going to be power output divided by power input, and efficiency is also going to be proportional. The efficiency is power output by power input. So power input into efficiency is going to be the power output. Power output is also proportional to 2 pi nt by 60, and where n is proportional, n is of course given by ns into 1 minus s. Okay, and torque is proportional to speed at torque is proportional to slip at high speeds, but it is proportional to 1 by s at low speeds. So all those aspects can be taken together to understand how the efficiency varies. Yeah, so these are some of the aspects that we discussed in this section, and I hope that most of the things are more clear to you, and you'll be happy doing any problems in induction machines. Thank you.